We may be watching a rare interstellar visitor. And the weird part isn't aliens. The weird part is what the observations look like. Dust that can seem sun-facing, a wobble that hints at rotation, and structure that feels too organized at first glance. So tonight, we hit the anomalies first, then we separate what's measured from what's assumed, and we end with a checklist you can reuse on the next object. If you like evidence-first space mysteries, hit like and subscribe. Alright, let's start with the anomalies. Not conclusions, not theories, just what looks wrong on first contact. Anomaly number 1 is the one that launches bad takes instantly. In some images, the structure can look backwards, like material is oriented the wrong way, almost like it's pointing toward the sun. And this is where the internet usually goes off the rails. People see sun-facing and assume intent. Propulsion, artificial, case closed. But pause. Here's the discipline. What are we actually seeing? We're seeing dust, brightness, and a viewing angle that can flip your intuition. A tail is not a rigid arrow. It's a cloud of particles shaped by sunlight and geometry. So, anomaly 1 isn't impossible. It's misleading. It looks impossible until you understand the geometry. Keep that pattern in your head because it repeats. When something looks backwards in space, it's usually perspective first. Now, anomaly number 2, the wobble. There are hints of a rhythm in brightness or structure, a subtle periodic behavior that keeps showing up. That matters because wobble usually means rotation. Rotation tells you about shape, and shape tells you what kind of body you're dealing with. So the wobble isn't a spooky signal, it's a handle, a way to grab the physics instead of guessing. Here's the trap. Controlled behavior feels designed, but rotation plus lighting can look like intent when it isn't. If we can estimate the spin, we can predict how features should change over time. That's how you turn a mystery into a test. Now, anomaly number 3, jets. Jets can look weirdly organized, directional, clean, almost engineered. And when people see directional jets on an interstellar object, the imagination goes nuclear. But again, pause. Vents plus sunlight heating plus spin can create clean structure even on very normal comets. So, the anomaly isn't a jet exists. The anomaly is what kind of jet, how stable it is, and what it implies for the orbit. Now I'm going to anchor the facts so this doesn't turn into vibes. Ground truth, it's interstellar because it's not bound to the sun. It's passing through on a hyperbolic path. That's why this matters. It's not a local rock with a weird photo. It's a visitor, and we get a short window to measure it. And limited windows create the next trap. When data is thin, people fill the gaps with stories. So here's the rule for this episode. We separate what was measured, what was processed, and what was assumed. Recap the 3 anomalies in one clean line each. 1. Sun-facing looking structure that can appear backwards. 2. A wobble that hints at rotation. 3. Jets that look too organized until you remember physics. Now here's the kicker. One of these anomalies has a boring explanation and one doesn't, at least not yet. The difference comes down to a single geometry detail. Part 2 is where we strip it down to the measurement layer. Part 2 is where we take the emotion out of it. Not because the story isn't exciting, but because excitement is how you get fooled. Here's the move. We drop down one layer. What do we actually have and what do we actually measure? Because an anomaly can come from 3 places: the object itself, the instrument, or the processing in between. If you don't separate those, you'll build a theory on noise. Start with the basic data types: images, light curves, brightness over time, spectra, what wavelengths are present. and the orbit, the trajectory through space. Most people obsess over the images, but the orbit is the spine. The orbit is where you see whether forces beyond gravity are acting. So our job in part 2 is simple: separate looks weird from is physically weird. Trap number 1 is contrast. If you stretch the image too hard, you can manufacture structure. A faint dust feature becomes a sharp line, a soft glow becomes a jet. A normal gradient starts looking directional and intentional. This is why two people can stare at the same dataset and report different anomalies. They're not disagreeing about reality, they're disagreeing about processing choices. So when you see a dramatic screenshot, ask the first question: what did they do to the contrast? Trap number 2 is compression and sharpening. Platforms love to invent edges. Compression breaks smooth gradients into blocks. Sharpening adds halos, and suddenly you get lines and ridges that feel physical but aren't. Your brain trusts edges. Edges feel like geometry, but on faint objects, edges are often just math artifacts from the pipeline. So if an anomaly appears only in one repost, one upload, or one edit, treat it as guilty until proven real. Trap number 3 is geometry itself. Dust does not behave like a solid flag behind an object. Particles separate by size. Sunlight pushes them differently, and your viewing angle can make a normal dust distribution look backwards. So when you see something that looks sun-facing, don't jump to engines. Ask, where is the sun relative to the camera, and what dust sizes would dominate what you see? That one geometry check collapses half the wild theories instantly. Now bring it back to the anomalies from part 1. The backwards look can be geometry plus dust sorting. The wobble can be rotation plus lighting. The jet-like structure can be real activity made sharper by processing choices. And here's the point: we haven't explained everything yet. We've only removed the fake mystery. Because the real mystery isn't, does it look weird? The real mystery is whether the orbit demands a non-gravitational force, and whether that force has a natural explanation that predicts future data. That's where ʻOumuamua enters the story. Part 3 is the comparison and the checklist. Part 3 is the comparison and the checklist. Because this is where people usually lose the plot. An interstellar object shows up, the data is limited, something looks weird, and the story becomes bigger than the measurements. So we're going to do two things. First, we compare this case to ʻOumuamua, the most controversial interstellar visitor we've seen. Second, we build a checklist that stops you from getting fooled next time. And I want to be clear about the tone here. This isn't debunking, it's calibration. Because space is allowed to be strange, but the moment you skip the method, you don't get truth, you get a vibe. So in this last act, we're going to move from what it looks like to what it must do. We're going to take the biggest lessons from the last interstellar shock and apply them before the internet writes the ending for us. Here's ʻOumuamua in 1 clean minute. It came in fast on a hyperbolic path. It was faint, and we saw hints of a non-gravitational acceleration. That phrase is where the drama begins. Non-gravitational doesn't mean impossible. It means something besides pure gravity is pushing it, even slightly. With comets, the usual suspect is outgassing. Gas and dust vent off the surface, and the recoil nudges the orbit. But with ʻOumuamua, the classic comet signatures were weak or missing in the way people expected, so the argument exploded. And here's the trap people fell into. They treated missing signature like a verdict. But missing can mean 3 different things. It can mean the signal is real but below detection, it can mean the physics is unusual, or it can mean the measurement model is fragile. So the story split into camps fast, and almost nobody asked the boring question first: what observations would actually separate these ideas? And this is the crucial point. When the data is thin, multiple explanations can fit at once. That doesn't mean the wild one wins, it means you need a test that can eliminate the wrong ones. So here are the three big buckets people argued about. Bucket 1, outgassing, just not in the obvious way. The prediction is that you should see consistent changes over time in brightness, spectra, or coma structure as it heats and rotates. Bucket 2, radiation pressure, sunlight pushing on a large area to mass ratio. The prediction is that the acceleration should correlate with distance from the Sun in a specific way. Bucket 3, modeling artifacts and uncertainty. The prediction is that as the orbit is refined with better measurements, the extra push shrinks, shifts, or even changes sign. Now here's what matters for us today. Those buckets aren't answers, they're test frameworks. They tell you what to watch next, what to measure next, and which result would force you to abandon a favorite story. And that's the part most viral explanations skip. They don't give you a fail condition. If an explanation can't be killed by new data, it's not science, it's mythology wearing a lab coat. Now bring that logic back to 3I/ATLAS. You don't start by asking, is it strange? You start by asking, what does the orbit demand? If the orbit is clean and purely gravitational, then most of the weirdness is optical and geometric. If the orbit shows a persistent non-gravitational term, then activity becomes central and you test how that activity behaves. This is why the checklist matters. It forces you to move from screenshots to predictions. Because here's the rule: if you can't predict a future observation, it's not an explanation yet. And there's another rule people forget. Your eyes are not instruments, they're interpreters. A bright core plus a faint dust feature can look like intent. A processing stretch can look like a beam. A single frame can look like structure. So when someone says it's pointing the wrong way, your next question should be, wrong relative to what geometry? Where is the sun? Where is the observer? What phase angle are we at? And what dust size would dominate that frame? That's how you stop yourself from mistaking perspective for physics. Here's the checklist: 5 questions you ask before you believe any anomaly story. 1. What in this claim is raw measurement and what is processing? If the anomaly depends on one edit, one upload, one contrast stretch, treat it as guilty until proven real. 2. Can geometry explain it? Where is the sun relative to the camera and what dust sizes would dominate what you see? 3. Does it appear across independent observations? Different telescopes, different nights, different pipelines. If it doesn't survive replication, it's probably not physical. 4. Does the orbit require a non-gravitational force? Not vibes, not images, the orbit. 5. What would we expect to see next if this explanation is true? If there's no clear prediction, you're doing storytelling, not analysis. And here's the bonus filter, the one that saves you hours. Ask, does the claim improve as more data arrives, or does it constantly move to stay alive? Real phenomena get sharper under better instruments. Fake certainty gets louder, vaguer, and more emotional. So, if a thread is mostly confidence and zero testable statements, you already know what it is. Now we close the loop. The point of these case files isn't to kill wonder, it's to protect wonder from fake certainty. Interstellar objects are rare, and that's why they feel mythic. But rare doesn't mean supernatural. It means we have fewer chances to learn, so every chance matters more. So here's the question I want you to answer in the comments. Which explanation survives the checklist best right now, and why? And what is the one observation, just one, that would change your mind? If you drop a timestamp or a specific measurement you're leaning on, I'll pin the best ones in the next episode. And quick one before you go. If you like Evidence First Space Mysteries, hit like and subscribe. It really helps this series keep going, because the next part is already in the works. Next episode, we'll take this checklist and run it on a fresh anomaly clip, frame by frame, so you can watch the method work in real time. No hype, no shortcuts. Just the simplest question that always wins in the end. What would we see if this was true? See you in the next one.